Ya estamos de vuelta ya, muchas gracias por esperar. Bueno, estamos en YouTube, en vivo, de manera totalmente abierta. Ya sabes lo que nos pasó lamentablemente con la otra plataforma, con Welcu. Increíble la charla de Jason, la verdad es que me voló la cabeza, así que vamos a tratar de invitarlo nuevamente a que ojalá esté acá con nosotros de manera presencial. Y ahora estoy acá con otra leyenda también, una leyenda hispana de Sudamérica, me refiero a Anderson Ramos, quien es emprendedor, es CEO, ha escrito también libros y es el organizador hoy en día de ROSEC y Mind the Sec, de más eventos también, pero me atrevería a decir que son los dos más importantes. Y en ROSEC en particular es la conferencia más grande de ciberseguridad de Sudamérica, que convoca a ¿cuántos? 5.000, 6.000 personas. Bueno, Anderson nos los va a decir ahora. Anderson, muchas gracias por tu tiempo, por apoyar 88. Ya tú sabes, eres parte de la casa, eres mi amigo también, así que bienvenido a 8.8 Leyendas Sandbox.
Gabriel, un honor, un placer muy grande de estar acá. Estaba acá asistiendo al final de la charla de Jason y para mí 2020, una de las memorias buenas que yo voy a tener es que fue el año de las rants de Jason Street en las conferencias de seguridad. Me encantó. Es un placer estar acá, pero principalmente un placer muy grande también presentar MATROSOV, que es como un monstruo de la área técnica. Y MATROSOV es un reconocido investigador de seguridad ofensiva, tiene más de 2 décadas de experiencia en ingeniería inversa avanzada, análisis de malware, seguridad de firmware y técnicas de explotación. Alex se ha desempeñado como investigador principal de seguridad en empresas tales como NVIDIA, Intel, pasó más de 6 años en el equipo del Intel Advanced Threat Research y fue Senior Security Investigator en la empresa ESET. Alex es autor y coautor de numerosos trabajos de investigación y es un orador frecuente en conferencias de seguridad, incluidos Recon, Zero Nights, Black Hat, DEFCON y otras. Además, X-Rays lo ha reconocido por su complemento de código abierto, X-Rays Code Explorer, que es desarrollado y respaldado desde 2013 por el equipo de ReHint. Y para sabermos además, porque MATROSOV es una leyenda, un pequeño vídeo, pero una información importante, MATROSOV tuve como un problema de horario y envió como un backup, un video para nosotros para que puedan acompañar la presentación. Le agradecemos muchísimo por el compromiso y vamos a saber, MATROSOV es una leyenda. ¿Por qué?
I'm Alex MATROSOV, and I'm leading offensive security research at NVIDIA. I'm mostly focused on the firmware and hardware research, and my team make an effort for make NVIDIA products secure, especially on the hardware and firmware side across of the different product lines. But today, I want to focus on the hardware security is hard and how hardware boundaries define the platform security. It's a very interesting topic, and I have much to say about this. But before that, I want to share about my experience. Actually, as I mentioned, I'm leading offensive security research at NVIDIA. Previously, I've been a principal security researcher in other companies like Cylance, Intel, and ESET, but I'm doing security research many years. And actually, most of my career actually been focused on security research. I did a lot of reverse engineering in the past, focused on advanced malware, and I can see actually how the reverse engineering technology is actually evolving and how the life of the offensive researcher is getting easier. We have a lot of interesting stuff get done already. We have now fancy fuzzers, memory sanitizers, and other stuff, but the defensive side, of course, also not sleep. And we have a lot of fancy mitigations, which is make very interesting challenges to bypass it. But let's talk about hardware and firmware side. We have a lot of security products and industry focusing on upper stack like operating system and virtual machines and cloud. But behind this, actually, we have a lot of things which can be focused on the attacking firmware and the hardware. And I would say a lot of modern persistence techniques especially focused on these particular points. And security visibility point for the industry, it's kind of like mostly focused on the upper stack and the boot process, but before the firmware actually close their execution, passing the execution path for the bootloaders. And we have a lot of challenges basically to make this down stack more secure. And if we think about the types of the persistence, we have a lot of things get done on the operating system level, and a lot of modern endpoint solutions actually focused on many different things, include the bootloaders and boot sectors, but I would say hardware and firmware currently the biggest blind spot being overlooked. We don't have enough signals coming from the firmware and the hardware to measure actually it is as we do for the operating system. And it's creating actually a lot of interesting points and concerns. I've been talking about that in the last year in my talk, The Advanced Threats Evolution and Researchers' Arm Race, because we actually have a lot of stuff coming from the hardware, but I don't see a lot of stuff coming from the defensive cycles, because actually we need to focus on the solutions, how we basically can prevent this kind of threats and actually detect them. We have three different worlds: firmware, hardware, and operating system, and it's actually separated. We have a weak security policies transition between of them. And as Matthew Green recently mentioned, we have the most interesting problems in applied cryptography right now, and all involve deployments of the trusted hardware. And it actually really defines, we have a foundation of our security tied to the hardware and firmware, but this foundation, it's not protected properly. So basically, I want to say the hardware threat modeling have a lot of interesting points, which is actually gain my concerns. So basically, how we define the hardware threat modeling at the moment. So basically, we focus on all the components separately. And also, we not define the boundaries where the hardware passing control or interact with the firmware. It's create very interesting concerns on how the attacker can basically attack the hardware from the firmware or opposite side. So basically, the threat model always focusing on something which is hardware or firmware, but not together. I see that a lot when basically people think on each tip separately on the platform. We will get there a bit later on the slides, but it's exactly why we need to focus and redefine the boundaries and threat modeling focused on the security boundaries across whole platform. Nowadays, it is hard to spot actually real boundaries between firmware and hardware because it's just a lot of connection points between hardware and firmware exist on modern platforms. And we really need to think on the hardware threat modeling and firmware threat modeling together. Because the number of issues actually increasing every year. And if you look on National Vulnerability Database with search query with the firmware keyword, we already have almost the same amount of the issues reported tied to the firmware side as the last year. So it is actually says a lot. We have a really increase of the vulnerabilities tied to the firmware, because in many cases, these attack surfaces, it is actually easy target and overlooked by many years, and we don't have much mitigation there. And also think about, usually hardware developed by one company, and in many cases, the firmware can be written by the third-party company. So basically, you have the chip, which is general purpose chip, can be used by the third parties for their products, and these third parties writing the firmware for this chip. That means they have actually some control on the top level of the firmwares, but all the boot ROM and actually hardware security features controlled by vendor of the hardware chip. And it is create a lot of weak points how the design can go wrong and create new attack surfaces or possibilities for the attacker. If we focus on the threat modeling and how the usual threat modeling is defined in the industry, basically it focused on analyzing the security requirements based on the platform diagrams, and they try basically create the threat modeling based on the known threats and attack vectors. And also, sometimes requirements can be missed something or overlooked before the real silicon actually came on the table, and you can really figure it out on the actual product, not just think about security and requirements before the product gets released, right? It is hard to find the real security problems in the platform on diagram based only on requirements, right? Also, sometimes in the industry, it's common when the vendors try to hide the firmware, obfuscate, or make it hard to find freely available online, right? Or make the firmware hard to analyze, remove the symbols and others. And in many cases, it can create some difficulties for reverse engineering, but it will never stop experienced reverse engineer to find the problems on this firmware. So it will be raising the bar, but really just a little. It's why I believe it's no need to count this way of security for protect the platforms. So not a binaries, please open the specs, and it will be basically make your product more secure, because overlooked problems can be spotted and reported by many researchers. Also, I've been writing the book Rootkits and Bootkits with Sergey Bratus and Eugene Radionov, and I really like this piece of art. So basically, look on this Kraken and this small boat with a person who tried to escape from this big Kraken, and it is usually security architects which is try to rethink of their threat modeling based on requirements, because in many cases they can overlook a lot of threats, and also if you not see all the boundaries, interconnections between them, and all paths, how the attacker can basically interact with some entity on the chip, it is hard to really make these requirements without the blind spots. It's why basically we need hardware and firmware security defines altogether, not hardware security. It's not this not equal the sum of the boundaries. It is really interconnection between all these boundaries altogether. We have a lot of different chips on the platform, but also these chips developed by different companies, embedded controller, TPMs, GPUs, network cards, base management controller, or power management units. So it interconnects around the UEFI system firmware, but all these firmwares inside these chips also developed separately by third parties. It is create a lot of concerns because basically we can't control all the boundaries in this case, but in the same way, it is crossing the path. As example, like a network card have an option ROM which is interconnect with the main system firmware, and it can create a lot of places where the attacker can reuse this path for basically attack the system firmware or opposite, attack from the system firmware the network card and persist there. It's why I believe we need to rethink the system platform security in the way when we think how the boundaries will be crossing. As example, we have mobile world where we have a Wi-Fi chip, but in the same way we have a baseband chip, but both communicated with application processor. So in the mobile world, we have this pretty similar problem where baseband chip can be one vendor, Wi-Fi chip another vendor, and application processor get done by the third vendor. So the problem is the same, but the solution it's also the same. So we need have more open specification and think on the security as a one picture, not different pictures for each chip. The system state transition between firmware layers and security boundaries defined by hardware, but frequently verified in the firmware. So it is create exactly the way where the boundaries is crossing, but in many cases, we not count this boundary where we making the threat modeling around the boot process on the hardware, because we say, okay, hardware boundaries defined inside the hardware, it's make them more secure. As example, root of trust, bake it inside the hardware. But if the transition is insecure, the secure boot can be broken. I really like this example of BootGuard, the technology developed by Intel, where we have basically following boot process. We have a CPU microcode, which is basically verify BootGuard ACM. ACM is a small piece of code which is executed before reset vector in not invicted memory, and ACM it is authenticated code model. So basically, after reset vector passed and BootGuard actually verified IBB, then K-manifest, which is actually verified initial boot block, and it's actually creating some transition of trust. And after that, initial boot block IBB verify other stages like Dixie and BDS. But think about the transition of chain of trust. It's kind of like a simplified picture, but we have some part of this transition signed by Intel, but also we have fused key by OEM vendor, which is control actually IBB and other stages after that. So basically, it is creating some really interesting situation where we splitting transition of trust between multiple vendors, and another side we also have really like security controlled by one vendor, which is create the specification, make it kind of obscure because it is not public, but it's shared with some OEMs vendors, which is basically in many cases don't have proper security teams. So, and it's why in 2016 I found multiple problems in the implementation bootguard and presented at Black Hat. So you can find my slides, Modern Secure Boot Attacks by Passing Hardware Root of Trust from Black Hat Asia and Opcode 2019, but also it's been part of research from 2016 Black Hat Vegas. But look on this picture actually, what's happening, we have also some inconsistency of security features, because think about, we need to update many machines in our networks. So in many cases, we need to disable some of the security technologies, which is make remote updates hard, or sometimes even more harder when we have this diverse ecosystem with hardware encryption, with disk drive encryption from different vendors, which is don't work together very properly, and we need just disable it sometimes, right? But if we back to bootguard, actually at my talk in OffensiveCon and Black Hat Asia, I was found some problem, which is actually been disabling bootguard IBB verification if we make some platform configuration flag available. It will be basically create platform manufacturing mode available, which is basically disable verification and open the door for the attacker to bypass all the transition on the later boot stages of UE5 firmware without any verification. Actually, it can be modified, and then basically it will be no signal from the system, the secure boot being not verified correctly any boot stage. So another interesting attack being reported by Tremel Hudson, where he found time to use, time to check with a spy flash, where early boot stage use ACM, and ACM actually read key manifest and other information from the spy flash. So here is different phases where it is actually appears on the boot stage, and where disable in non-invicted mode cache as RAM get done, right? So, and we can see actually init of DRAM and load RAM init model happening earlier. So basically, it is making some possibility for the attacker to modify something before it will be verified. And we can basically fake it, this information, and verification will be get exactly information the attacker wants, but the system, and it will be pass the system verification. Here is a GitHub link where this issue been fixed. The interesting thing, not many vendors actually apply this fix, and this issue available broadly in the wild with many vulnerable systems, but it is need a physical access for the attacker to make this time to use, time to check race condition attacked. Complexity of the modern firmware supply chain is very complex. And not controlled 100% by a single hardware vendor. It's why it's creating a lot of problems for whole ecosystem, because we have one part of the code, like an Intel reference code or EDK2, coming from the one side. We have a Phoenix, American Megatrends, or inside vendors of usual UI5 frameworks for developing the firmware from another side, but also we have part of the code which is developed by original manufacturer equipment. So, and also all this code need to be patched, and the patches coming from the different sources, which is create a lot of inconsistency. And I would say in this way, only Apple actually control all the way of their firmware updates. What about good old days with operating system bootloaders? So if we think about the legacy boot process, we have the BIOS code, which is passing control to master boot record and bootstrap code like a volume boot record and initial platform loader. So which is passed actually control to boot manager. And in UEFI, we have UEFI firmware passed the control directly to UEFI bootloader, which is actually passed the control to WinLoad UEFI. So boot manager UEFI and WinLoad controlled by the operating system. But what secure boot will save us all, right? In many cases, yes, but also we can see how UEFI ransomware actually appears recently, which is just use patches for boot manager and WinLoad UEFI, which is actually create some possibilities for the attacker to lock the system in the boot process. But of course, it will be also blocked by secure boot, and it's mostly focused on Windows 7 system, which is already quite rare applicable. But still, we have this inconsistency in signing process of the bootloader. And if you remember, it was a few months ago, the discussion around the signed bootloader by the Kaspersky, which can be abused for basically loading the next stage bootloader modified by the attacker. And actually, this signature been revoked, but it was not exactly patched on all the systems. It was just revoked and provided optional update by many vendors. So what if signed bootloaders can be not trusted? It is exactly actually why security industry learned a lot of lessons back to early 2000s when we learn when the signed binaries doesn't mean trusted, but the same thing actually we need to think about on the bootloader side. Signed not mean or not equal to be trusted. Also, that remind me in my 16100 golden key issue where the vulnerability can be used for the feature bypass, and attacker can install modified boot manager, so and bypass secure boot on the Windows. So this issue been presented on the DIFCON at 2016, and also you can find more information based on this link, but it's pretty similar on the problem which is being discovered pretty recently. So we blindly trust anything which is signed and come from the trusted source. As example, bootloaders or like firmware updates, if we download them from the trusted website, that's mean it's a trusted source, right? But also think about one more interesting vulnerability been recently spotted, boot hole. Basically, what happens if we have signed bootloader, but this bootloader contains some vulnerabilities or inconsistency of the trusted chain. So it's exactly what happens, and also this kind of vulnerabilities can contain the way for bypassing the clouds. I mean, cloud security, because if we abuse the platform boot and persist inside the firmware, we can go upper the stack and bypass many layers of security there. So I would say virtual machines encryption, memory isolation, and memory encryption technologies really helps, but it's not spread everywhere yet. And it also has a lot of limitations on older platforms. So as we can see, here is a grab issue, which is allow to boot any bootloader on upper stage, which is basically arbitrarily controlled by the attacker in this case. And it was spotted on HP ProLiant servers earlier this year. The diversity of the open source ecosystem actually bring more inconsistency to the boot process on the late stages. And many vendors, which doesn't have a proper security teams, can recognize this problem, or actually this supply chain make a lot of difficulties to patch these issues in the right timing. Think about on the embedded world, we have boot ROM usually baked inside the silicon, and we have a multiple stages happens after that. So what if one of the stages will be affected to the issue in the runtime? So in many cases, we have this transition of trust, which is basically focused on boot ROM inside the silicon, which is verifies the loader and then passing the control in runtime to the next stage's loaders. So in this case, if it will be issue in the silicon boot ROM, so the attacker can bypass any upper layers. But what if it will be issue on the next stage loader? So if the issue can be exploited after verification or even on the upper layers, so that's done, right? So because the transition already happens, and after that the loader became the root of trust, and after loader verifies the bootloader actually gets this transition of trust on their stage. It's why it is important to have the consistency of the secure boot, and also we need to make all this supply chain ecosystem for embedded bootloaders more consistent. Also, what can go wrong, right? So with a silicon boot ROM, it's remind me checkmate issue, which has been recently found on boot ROM of the Apple devices. But I will not go deep on it because it's not a topic of our talk. But what I want to say, it's why hardware security can be very hard in this case. This issue baked in silicon, it's hard to patch on other layers, and then basically it will be stay forever in this device. Also, another example, it is a 2019-90, which is basically CSME, Intel CSME initialization stage issue. Basically what happens, it is a very interesting issue when CSME turns on paging and maps ROM in very early stage. And IOMMU basically memory isolation, it's turned on too late, and the attacker can remap these execution pages to arbitrary physical device, even spy flash, which is actually opens the doors for the attacker to attack CSME. It is very cool bug being spotted by Positive Technologies folks, but also it is example of the silicon bug, which is actually hard to patch because it's being created in the part of the boot ROM which is invictable and not can be patched. It's why in many cases we need to see the full picture and all these transitions to understand where we need to focus on security validation and verification, because as a offensive researcher, I always try to find the weak spots, and in many cases, the weak spots tied to the hardware. The boot time software supply chain only increasing actually the complexity, because if we have all these bootloaders from the open source, it's very hard to patch, because in many cases also third-party vendors modify them and provide their versions to the market. So basically you can't control the supply chain when original version of U-boot or grub release something, right? You need to patch your own software based on your modifications. I really like this picture from the talk of Rob Wood from the Platform Security Summit last year, which is talking about the complexity of the attack surface increasing on the operating system level, but in the same thing, it is decreasing on the firmware and the hardware level, because we do have a lot of fancy mitigations on the software stacks, but it is really limited on the down layers like firmware and hardware. But what if root of trust will be baked in FPGA or silicon? It reminds me very interesting issue with finding from the Red Bound security last year with Cisco Trusted Anchor, where on the Cisco devices, root of trust being baked on the FPGA. And they found the way how they basically can attack and modify the bit stream and basically bypass the secure boot and gain the persistence on the Cisco routers and devices with a trusted anchor. But on another way, it was also a little bootloader on Max 10 FPGAs from Intel, and it was an interesting issue where the attacker can use race condition attack on the boot ROM. What about OpenSilicon? How it helps to reduce the risk? Actually, it's create more transparency on one side, but also how many of this transparency can be reused by the vendors in the right way. Think about, so we have a traditional root of trust on the embedded devices where in most of the cases, the root of trust tied to boot ROM. I really like the concept of Open Titan, where most of RTL code, it's a transparent, but on another side, it is create a lot of complexity for the developer to make this properly implemented and also supported on their devices. We blindly trust anything which is baked in silicon in many cases, and also we trust blindly all our hardware. Think about. But we have a RISC-V revolution coming, right? So, and basically where we have all these open standards, and what is actually concerning me, it is currently we have a lot of actually silicon and RTL open cores available for the third parties. And you basically can reuse a lot of design from the other vendors like NVIDIA or Western Digital. It is available on open, with open RTL and Verilog. But problem here, a lot of companies, small companies, can reuse these IPs without proper validation. And it's basically create the silicon supply chain hell where we have on one side a lot of open source and transparent silicon, but on another side, it can be reused without proper validation. Also, we have this problem with counterfeit devices and hardware implants. It's actually not a rare thing as you can think about. I really like recent F-Secure Labs report about counterfeit Cisco devices with some open GTAC pins and some pins for actually bypass all the trusted boot on the platform and many other things. We really need to rethink meaning of hardware security in realities of modern threat models. And as offensive researchers, we need to focus on fixing the hardware trend modeling on the hardware, right? Finding the issues. And in many cases, my threat model is different from the threat model which is think from the vendor side. I would say in many cases, my assessments on the platforms, it's where the threat modeling meets the realities. Hardware security is hard, but we need to make it more secure in the hard way then. Thank you very much for your attention.
So we just had an excellent presentation by MATROSOV. Now we'll be answering some questions you guys just did. So Alex, thanks for being here with us for the Q&A session.
It's my pleasure.
Yeah, you're welcome. The first question is, how often, we have a question about, we couldn't understand really well this question, but I think the person is asking for supply chain controls for firmware in general, if simplicity helps.
Yeah, I think it's actually a very good question, and it's covered some of the thoughts from my talk. So actually, the problem is, as example, for UEFI ecosystem and for x86 platforms firmware, ecosystem is very complex. And as example, compared to the single ARM chips, it's much more simpler. As example, if you have one vendor like Apple, which has developed the hardware and also the firmware, the supply chain much more simpler because the single vendor develop the firmwares and ship to the customers. But if we talk about like usual case with x86 servers and client platforms, it is like Intel reference code for the firmware. It's shipped for the third-party vendors like American Megatrends or Phoenix. which is developed the firmware frameworks, and these frameworks used by other vendors to develop their firmwares and ship to the end customers. And think about how many points of this supply chain you have, and actually if vulnerability happens in Intel reference code, Intel need to be responsible for this vulnerability. If vulnerability happens in American Megatrends or Phoenix, these guys should fix it. But problem is also they have kind of like support time. And as example, if the systems for particular vendor is out of support for this firmware, so these issues will be stay forever. So yeah, it's very complicated, but I hope in the future we can fix it.
Excellent. Another one from Alfredo Diaz. How often are the hacking threats that need a physical access to a computer?
Oh, that's an interesting question. So I would say usually, actually, if we talk about the actors, threat actors, they prefer remote attacks. But if it is like a particular target, as example, you go into the conference and somehow you get interested by particular people and they want to attack you. So you leave your laptop in the hotel. So basically, if they can get access to your room, the physical access will be give a lot of possibilities for attack your computer. As example, bypass login screen, install some persistent implant to your firmware, and etc. It's a lot of steps can be done in this way. Also, if back to the previous question about the supply chain, so basically you buying the server, let's say from Amazon or whatever company, so it's a long way before it's shipped to your data center or your office, right? So basically, I would say if you get any hardware and want to install in your data center, make a simple provisioning, download original firmware and flash it directly to the hardware before you install this hardware to your data centers. Or if you get a new laptop, so yes, it is new, but you don't know what happens on the way to you. So be sure you have original firmware on this laptop. Make sure it is nothing malicious there. Yeah.
Yeah, so in the first scenario, I was wondering if you were invited to the Kaspersky Researchers Invitation-Only Conference, you probably should be really concerned with that particular scenario.
I would say I would be concerned with any conference which is security conferences. It's not about the conference; it's just about like who can participate, right? So
yeah,
and also this year we stay in remote, right? Virtual conferences save us all.
yeah. I have friends that they say that the best thing with security conferences is that don't take your machine there, leave it at home. So, and we have another question here. I think it's a follow-up question on your answer about supply chain attacks. That is, but if we need a company to at least to make the chips and firmwares, how can we feel safe nobody's spying on us or controlling our data?
So yes, that's actually a very interesting question, because I would say the hardware companies need to be more transparent, because basically it's a lot of things which is happening in silicon is just a black box. Think about, as example, Intel microcode. It's providing most of security features available on the platform. As example, it's even implementing some of the root of trusts tied to the platform. So, and we don't have any understanding what's happening there. We don't have any provisioning, just Intel control, Intel ship updates, etc. So it's create a lot of complications and concern. It's not only about Intel. It's about any type of the silicon. Companies usually try to be more restrictive to what they share on the documentation. And I would say in this case, we need kind of like gaining more transparency on the hardware, because it will help us also to fight the future threats. Because in current state, as example, endpoint solutions have a zero visibility on the firmware and hardware. So it's creating huge room for the persistent attacks which is happening on that level. And as example, collaboration between the companies who develop in security solutions and the hardware vendors to create this kind of like transparency or some indicators which we can gather from hardware and firmware levels, it will be very helpful.
Excellent. Alfredo had another follow-up question, but I think you somehow address it. And then we have our last question. If UEFI and Secure Boot are not secure anymore, what settings, features, or tools can we use to mitigate that risks?
So it's actually a very hard question, because I would say if the firmware is already hacked, basically, let's say the platform not boots in one way, right? So it's the stages of the boot process. And between these stages, it is a transition of the chain of trust. And as example, even if we have a baked to the hardware root of trust, it's make a transition to some of the stages which is tied to the firmware, and it is already only the software controlled. And so basically, if the firmware is controlled by the attacker, it's really hard to make this platform secure. I would say it's almost impossible, because the transitions on the later boot processes happens inside the firmware. And basically, when your operating system starts, and basically some code injections which can happen in the bootloaders controlled by the firmware, right? So basically, attacker have a full control on the upper level boot process, and I would say, yeah, I will not trust the system.
Yes. So with this last question, we just finished MATROSOV's presentation here at 8.8. I do miss a lot of physical events, and because of that, I just figured out a way to applause our speakers. So thanks a lot, MATROSOV, for being with us.
Yeah, thank you very much. I really appreciate the invite for this conference. I really want to make it physical, because I never been in Chile, but maybe next year. Thank you, guys. It was awesome.